In this video, we'll understand what Docker is and why it is so popular. So before understanding Docker, we'll try to understand how a traditional development workflow works. Okay, so let's say you're building a Spring Boot application. So normally when you build a Spring Boot application, you do a below setup in your machine. For example, let's say in your local machine, let's say using a Windows machine. So you need to install all the softwares. Let's say you're installing a Java JDK, we need to install Maven. And let's say your Spring Boot application requires a database here. We need to install the database as well. And let's say your application using a caching mechanism, so you need to install Redis also. We do set some environment variables so that our application works fine. Okay, so let's say this is a very typical setup. We have window machines here, and all your software application are installed in your machine. All the configurations are set. Okay, so you write the code, you test them using your unit testing, and everything works fine perfectly on your machine. And let's say you want to test your application in a different environment, or let's say you want to share your code with the another developer for testing, or you want to deploy it in your QA environment or the production environment. And suddenly in that specific, let's say in QA environment or the production environment, some issue happens. So this is a very famous problem. Like it works in my machine, but it doesn't work on a in the production server or in any other setup. So what does that actually mean? So your code might be correct, but the environment is different. Okay. So why environments differ? Let's say this was your setup which you in your local machine, and let's say you are testing it in QA machine. Okay, so what may happen, the environment in QA machine itself might be different. For example, let's say you are having JDK 17 here, but in your QA environment you may be having a different JDK version, or you may be having a different database version, or you may be missing some configurations, Maven may not be installed, your Redis may not be installed. So you may face such issues, and the port which you're trying to use may be already used, right? So these are some of the problems which you can face in a different environment. So what does happen? So your application may fail to start, or you may get some runtime exception, or SQL binding issues you can get, or a port binding issues you can get. Okay, so these are the some common issues which you face when you try to run your code on the machine. Okay, so these are some examples which I have highlighted. So let's say Java version mismatch can happen. Okay, you're compiled with Java 17, but your server has Java 11. Your MySQL driver works locally but fails on the server. Linux and Windows file path may be different. The Redis itself may not be installed, or your app is already using the port number, or you may have some manual setup issues which you might have done. So how did we try to solve this problem? So to avoid all this problem, you could have documented all the steps. You need to install so and so softwares. You need to create the database, and you need to set up the environment variables, and then you run the application. So you documented all the steps, and you gave these steps to your operations teams, or a QA team, or the production teams. Okay, but it may happen that some steps might be missed by the team members, right? They may Human error can always happen, and they may miss some steps, and some issues can happen in that specific environment. So what are the other option we use the other option which we tried is a virtual machine. Okay, so what exactly is a virtual machine? So a virtual machine is a full computer inside another computer. What does that mean? So if you see this diagram here, this is the virtual machine. So we have a host machine. On top of that host machine we have a hypervisor. So what does this hypervisor do? So each virtual machine has its own operating system, has its own kernel, and has its own libraries. So all of them are running on a hypervisor. So what is a hypervisor? So a hypervisor is a software that splits the hardware into multiple virtual machines. Okay, so this hypervisor is splitting this machine to multiple virtual machine, and each virtual machine is having its own operating system. So this is a typical virtual machine architecture which was there. So now we have a physical hardware, then we have the hypervisor, and then top of that hypervisor we have the virtual machine with their own operating system. So they had some benefits, like they were strongly isolated. Each virtual machine had its own operating system, but this was good for the legacy application, not for something like microservice application. So what are some of the issues with the virtual machine? So each virtual machine has its own full operating system, which can occupy a lot of space. Okay, so it can take a lot of GBs of RAM, and since it had its own OS, it can take a lot of time to start up. The startup time was in minutes, so it's not very scalable. It's not very cloud native in nature. Okay, so that is where the Docker comes into the picture. Okay, now we are going to introduce it. Okay, so what problem this Docker is trying to solve? Okay, the Docker mainly solves this environment inconsistency problem. So it tries to answer this question: what if I ship my application along with everything it needs to run? What does that mean? So instead of saying install this Java, install MySQL and configure this, you just say run this container. Okay. So what was the problem in virtual machine? So each virtual machine was requiring an operating system. But do each app really requires an operating system? It only requires a file system, network, CPU memory limits, process isolation, dependency isolations. Okay, it doesn't require the complete operating system to run. Okay, you can run multiple isolated application and they can share the same operating system on the kernel. Okay, this is how the architecture of the container looks like. You can see it in this diagram also. So we have a Docker, we have a host machine, and top of that we can have the Docker engine, and on top of that Docker engine we can run multiple containers. Note here, in the virtual machine, each of the virtual machine was having its own operating system, but here in Docker we don't have that operating system here. There all of them are sharing the same operating system using Docker engine. Yes, this is what I was referring to. We have physical hardware. On top of that, we have the host operating system. Then we have the Docker engine, and on top of the Docker engine, we have the containers. And containers are having both the application and their libraries. So why containers are better than the operating system? Because they are sharing the OS system. They don't have the operating system. Each application doesn't have its own operating system. They are sharing the operating system, and due to this it can start the containers can start in seconds, and their size is only in MBs, not in GBs, because you don't have the operating system inside. And scaling is easy in compared to the virtual machine because they're very lightweight in nature. So this is where the Docker definition comes into picture. So this is a formal definition of Docker. Docker, what it does, it packages an application and its dependencies into a lightweight portable unit called as a container. So what does your container include? It's very important. It includes your application code, your runtime, your dependencies, your OS level libraries, and all your configuration. And due to this, it runs the same everywhere, in your developer machine, in your QA environment, in your production environment. It runs the same. This is a comparison with Docker and without the Docker. No setup is required, no manual setup is required here. It's OS independent, and if you have any issues, it's very easy to reproduce. It works everywhere, and onboarding is very fast. So the key takeaway here is Docker eliminates its works on my machine problem by packaging an application and its entire runtime environment into containers, and that behave consistently across development, testing, and the production environment. Okay, these are some of the core benefits of Docker which are highlighted, okay, which we already discussed. First is consistency across environments. Build once and run everywhere. So the same container runs on the developer machine, test server, and the production. It eliminates work on my machine problem. All your application dependency and runtime are packaged together. So there is no dependency mismatch or a version mismatch. They are lightweight compared to virtual machine because there is no need for full OS per application, and they share the OS kernel, and they can start in milliseconds, right? Because they don't have the OS full OS per application, and it's very ideal for microservice and auto scaling. And they are highly resource efficient. They have better CPU and memory utilization than the virtual machine, and you can run more application on the same hardware. Docker looks very simple from the outside, but internally it uses a powerful Docker architecture. So these are the following components of that specific architecture, and each component has its own responsibilities. So this is a typical Docker architecture here. Okay, right from starting from the user who types the commands to the Docker CLI to the Docker daemon. Then there is the container daemon, and then there is the runtime container and the kernel. We will have a look at each component in detail in a very simple language. Okay, so Docker follows a layered architecture here. So it consists of the following components, just as I mentioned in the diagram. So let's get started with the first one. Is a Docker client. So what is a Docker client? So Docker client is nothing but the command line tool which you interact with, where you type your Docker commands. For example, I have a command line tool here in the Windows terminal, so I can just type any Docker command here like Docker images. This will list all the images of the Docker. So this is the CLI tool wherein I put my when I mention what commands I need to type. So this is the CLI tool here. So we can run any commands here. So the client here does so the client which is here, right? It does not create the containers. It only sends the commands to the Docker daemon, right? So I'm typing the commands in the Docker CLI, and it is sending the commands to the Docker daemon here. Okay, client talks to the daemon using a Unix socket. So we'll move on to the next component, which is nothing but the Docker daemon, right? As the name suggests, it's the most important component of the Docker architecture. So also called as Docker D, it is the Docker daemon, the main brain of the Docker architecture. So this exposes the Docker REST APIs and implement Docker specific features. So whenever we type a command, okay, it exposes a REST API, and all the commands are handled by the REST API. So it handles all the Docker CLI commands. It also takes care of building the images and pull and push of images to the Docker registries, management of the networking of the containers, management of the volumes, supporting the Docker Compose. And let's say you want to authenticate with the Docker Hub or any other Docker registry, that is taken care by the Docker daemon, and high level container management. So it does not create the container on its own, it delegates the responsibility to the next step. Okay, so from the Docker CLI, all the commands are gone to the Docker daemon. So it handles all the image management, volume, and all that stuff. Also handles pushing and pulling from the Docker registry. So we'll come back to the Docker registry later. But yeah, this is what it handles, and it anything related to the container management or creation, it is going to delegate the responsibility to the container team, which is the next component. So any command if you type, so in the Docker daemons, what exactly it is trying to do is it's going to pass all the flags which is mentioned in the command. It validates the command, sets up any networks or volumes, decides which image to use, and asks the container daemon to create or start the container. So then we move on to the next one, which is nothing but the container daemon. So as the name suggests, right, it's an industry standard container runtime. Okay, it is not Docker specific. The main responsibilities of this container daemon is to manage the container lifecycle. Creation, starting, stopping, deleting, all this thing is taken care by the container daemon. And this is what the container daemon is going to interact with the runtime container. And this is the component which is actually going to create the container for it. Okay, and it is going to handle the low level container task. For example, let's say a Docker daemon says start this container. It is going to delegate the response to the container daemon. So from the Docker daemon, it is going to go to the container daemon right here. Okay, and so why did Docker introduce this container daemon? So before Docker, we had a huge monolithic daemon. It was very difficult to manage, and it was very hard to integrate with the Kubernetes. So the solution was the solution was to split those responsibilities. The high level responsibilities will be taken care by the Docker daemon. Any low level responsibilities of container management will be taken care by the container daemon. Now the Kubernetes can directly talk to the container daemon, and but Docker internally still uses the container daemon. So we moved from the Docker daemon to the container daemon, and container daemon delegates the responsibility of creation of containers to the runtime component, runtime container, which is the uh, next component. So also called as runc. This is a low-level container runtime which is used by the Docker to actually create and run the containers on the Linux. So what does this runtime container do exactly? Okay, so this is the one which is actually going to provide the isolation support or the container isolation it is going to do. So actually it uses the Linux namespaces which are provided by the kernel. So this namespaces decide what the process can see, right? So the isolation is provided by the kernel, but it uses the namespaces. So what kind of isolation it provides? It provides the process isolations, also network interfaces, file system mounts, all inter-process communication, host name. So all this isolation, which is required by a container, is provided by this Linux namespaces. Then similarly, we have C groups. Okay, and so this controls how much how much a process can use, or how much CPU memory or IO limits a specific container can use. So this limitation is set by the C groups. The resource control is set by this C groups. Say, for example, if you are running like how much memory you want or how much CPU is required. So all those things are again decided by C groups. But again, it is provided by the kernel. It just uses it. Runtime container just uses this, which uses this facilities which are provided by the kernel. Also, it sets up the container root file system, start the container process, and it talks directly to the Linux kernel. So as I mentioned earlier, right? So this runtime container does not provide the isolation to the container itself. It is just uses the features which are provided by the Linux kernel. So why does the Docker require the runtime container? So before runtime container, Docker had its own runtime. Okay. Later, Docker donated this runtime to the Open Container Initiative. Okay, so it is runtime container is the OCI reference implementation. So it works with both with Docker and Kubernetes, and it makes the container standardized and portable. As I mentioned, this runtime container directly talks with the Linux kernel, which at the execution layer, right? For example, this is the main Linux is what is going to provide the process isolation, and it also implements the C groups, which provides a resource control, file system abstraction, networking. All this are provided by the kernel. So container is nothing but the normal Linux process, just which are isolated using the kernel features. So at the end, we have the container, and the app is running as a process ID one inside the container. Any logs which are present are streamed back to the Docker daemon, and the status also is tracked by the container daemon. This is what we have discussed. The okay, initially it builds the Docker daemon actually builds the images, manages the containers, networking, and the volumes. Container daemons manages the container lifecycle. It is the runtime container which actually create and runs the containers with the help of the Linux kernel. Now all the isolation, the resource control is provided by the Linux kernel. So Docker cannot run containers without the runtime containers. So in the diagram which we saw here, right, we had a Docker daemon. It was like for it was pulling and pushing the images to the Docker registry. So let's try to understand what is a Docker registry here. So what is a registry? So it's nothing but the storage for the images. For example, Docker Hub, AWS Elastic Container Registry, and GCP Artifact Registry. So this is a hub where all the images are getting stored. So Docker daemon can also pull the images or push the images from the registry. So internally, all the images are transferred layer by layer, and if at all it is existing in your local, those layers are skipped. So this is a Docker Hub, okay, official website of Docker Hub. And if you want to, let's say, pull or push an images from the Docker Hub, you can use this command here, right, which is mentioned here. And all the documentation of the images is mentioned here. And if you want to pull images from there, you can use pull the images using tags also. And yeah, this shows all the details if you want to refer for any images per se. Okay, coming back to here, so this is a complete picture here. So users runs the command. So Docker CLI actually sends that commands to the Docker daemon, and it is going to check if it is trying to get some images. It is going to check if the images are already present locally. If it is not present, it is going to send the request to the Docker registry. Okay, and then it is put after from the Docker registry. It's going to download all the image layers and verify the checksums and store it locally. So once we have the Docker images, then it's going to send the request to the container daemon here, which is going to do all the image unpacking and the snapshot, and it's going to create the container metadata, and then it's going to delegate the responsibility to the runtime container here, which is going to create the namespaces, apply the C group, set up the root file system with the help of the Linux kernel. So at the end of the day, we have a container process started with the process ID 1, and then we have the running container. So today I will explain Docker images from scratch, how Docker images are built, where are they stored, and the most important Docker commands you should know for working with images. As we know, Docker packages an application and its dependencies into a lightweight portable unit and run it as a container. But do you know, like, how do you package this application, all their dependencies and its runtime environment? So to do that, we need to give some instructions like how to package your environment, dependencies and the application. And also when they are packaged together, we also need to store them as a package. So that's where Docker image comes into picture. So what is a Docker image? So Docker image is nothing but a read-only package that contains everything needed to run an application. An image can contain all the application code, all the runtime libraries, and the dependencies. It also can contain the environment configurations which you require. It does not include your kernel or running processes or any runtime state. It includes all the stuff which your application needs to run in an isolated environment. So Docker image is nothing but an application plus dependencies and their runtime. But this Docker image actually follows something called as a layered architecture. Okay, Docker images are made of multiple layers, actually, which are stacked together. So let us take this as an example here. So at the base layer, if you see here, we have the Ubuntu or the Alpine OS layers we have at the bottom of it, and then at the next layer we can have our Java runtime environments, and top of that any other dependencies which you require, and at the end we have something called as a container layer where we package all your application, all that stuff. Okay, so this is what I mean by the layered architecture. So each layer is a read-only layers, okay, and all of them can be cached, and all of them can be shared across different images also. So how do we create each of the specific layers here? Okay, so each layer in a Docker file creates each instruction in a Docker file can create one specific layer. So I have a Docker desktop installed in my Windows machine. So if you go to something called as a Docker Hub here, it contains all the images which you require for running it as a container. For example, let's say you require a Redis image, so you can find it in a Docker Hub as well. So here it is officially maintained, and you can go and pull any images of any versions here or any tags given here. Okay, so let us try to pull image here using a Docker command. So let me go to my machine here and let me try to pull a Docker Redis here. Sorry, I'm just putting the Redis image here. Now if you see, this Redis image is not locally stored. As I mentioned, it's a layered architecture. So it is trying to pull it from the Docker Hub here. And you will see now that layer by layer it tries to pull all the images here. So it is pulling from, see, layer by layer, it is trying to pull all the images here. Now you could see the image has been pulled successfully from the Docker Hub, and it has been pulled layer by layer here. So let's say, let's see if the images are present here. So for that, you need something called as Docker images command. So this is going to show you the image which has been pulled from the Docker Hub. And let's try to pull a different version of Redis here. So let us go to the Docker Hub and let us try to pull version number 8.0. Okay, so for that you can give the same command, but here you mention the version number or the tag name here. So it is going to pull a new version of the images. Now if you see here, the difference here is, if you see, the layer was already existing, so it hasn't pulled that specific layer. Initially we pulled the Docker Redis here, so all the layers were pulled from the Docker Hub. Since some of the layers were already present, so if you try to pull the same image with a different version, so if it is built on the same layer, that layer won't be pulled again because it is cached locally. So that is what that is what actually means caching here. It's a read only, and it is cached, and it can be shared across the images. The layers also can be shared across each image. Okay, and this is a command to pull an image from a repository. So here the repository is a Docker Hub, which we went. Okay, so since we have pulled an image from a repository, can we just create our own image here? So to create an own image, we need to give some instructions, and we give those instructions in a file name called as a Docker file. So it's a text file filled with instructions. So here we give all those instructions, and each instruction is going to create a layer. For example, I have a Spring Boot application here. Okay, I have a Spring Boot application, and I've actually built the application, and I've packaged the application with this specific name. And if you see here, I have a Docker file here at this Spring Web layer, at this specific directory layer. Okay, I have the Docker file here, and the Docker file contains all the instruction here. So it is going to pull an image from this base image, and it is going to create this directory, and it is going to copy the built jar which I have done here from the target folder, and it's going to copy it in app/app/ in that specific location. It is going to store this specific image, and also mentioning that the Spring Boot application, when it starts running, right, it is going to be listening at this specific port. So when we run this image as a container, so this is the command which is going to be executed. So it is going to run a Spring Boot application with this command. So we are going to give all these instructions in a docker.file to create, first of all, create the layers, and then we have to package this is our application code. So we are also packaging our application code. We're also giving instruction as to on which port it should listen, and also we are giving instruction as to what to be done when an image is run as a container. Okay, so for that purpose, what we need to do here is, so since this is an example which we have mentioned, okay, so how do we run it? So this is what I already explained, that from it is going to pull the base image, it's going to create the directory, it's going to add the application layer, and it's going to entry point is going to start the application layer. So Docker is going to catch each layer so that rebuilding is very fast. So how to build it? So we can just build it using this command, docker build. You mentioned that what is the name of the image which you want to give. Either you can give the name or you can give the version number, and dot means that you are going to read from a Docker file, and Docker file is present in this location, the current location. So I am at this location. So if you see, I have a Docker file at this specific position. So I'll do a docker build -t. I'm going to give it a name, Spring Web application, and Spring Web application. I am going to read the instruction from the Docker file which is present at the current location, and the Docker file is present here. I'm going to run this. So now right now it is buildings. If you can see here the instructions which I mentioned, right? Like you have from this base image you have to take. So it is downloading the base image, and it is going to the creating the work directory, and it is copying here copying the application Spring Web jar which is there in this current directory. Now, so you can see all the instructions which I give from the Docker file are been executed step by step here. Okay, and you can see if you can check whether the images are created or not. So we can see the Spring Web image which we created using Docker file, and this is the size of that specific image which we have already created. Earlier also we pulled those images from here, right? And this is mentioning the size of that specific image here. So this is how we can create an Docker image from the Docker file, as I mentioned here. So it's going to read the instruction from right from the top to the bottom, and it's going to execute each instruction, and it is going to create a layer per instruction, and it is also going to cache each layer, and the order of the instructions matters. Okay, so let's say if you want to update an image also, right, we cannot go and just edit the image. Okay, you need to create a new image version. For example, let's say you want to build again. So what we can do here is we can just go back, and you have to build an image again. We can just mention a new version number, right, like this. Okay, and you can create a new image out of it. So right now I'm not doing, but this is how we can do it. Okay, so these are the common instructions which can be put in the Docker file right from the from instruction. If you want to run any command during the build process, you can use the run command. If you want to copy your executables into the image, you can use the copy command. You can set the working directory. If you want to set any environmental variables which you want, we can set using the environment. If you want to expose any your application port, on which port your application which is running should be exposed, that you can mention using the export. If you want to run your it as a container as a fixed executable, you can mention it as an entry point, or a default command which you want to run when this image is run as a container, you can mention as a command. So there are different rules for image naming and tagging, right? For example, let's say if you want to push this image into a Docker Hub, so this is how we can do it. You have to mention the repository name which you have created. So once you log into your Docker Hub, right, let's say I have Docker Hub here, so I have created a repository here as Harish Gowda 84. So whenever you're creating an image and you want to push that image into the Docker Hub, you have to mention your repository name first, and then slash you can mention the application name, and then you can also mention the version name, for example here. Okay, you can mention the version name also here. Okay, and so let us first try to delete the images. So for deleting images, you can use a command docker rmi, and you can mention the ID here. So you can just mention your ID. So it is going to delete it. So let's say if I want to push this image into my Docker Hub, so for that purpose, I need to mention my repository name in the Docker Hub. So right now it is Harish Gowda 84, and then Spring Web. I need to ensure that I don't have that application here, so it is new. So I mentioned doc Harish 84 Spring Web, and then I'm creating this image now with this name. Okay, you can see the image got created. Yes, it has got created here. So let us push this. So before pushing, you need to log into your Docker Hub. Okay, and then only you can push that image. Okay, you can log into your Docker Hub, and in your Docker Hub also you should have this. You should be Docker desktop also. You should be logged in here like this, and then only and then so okay, then only you are able to see all the images. Then only you're able to push those images. Okay, so let me just push this image first. Docker Hub to Docker Hub. So Spring Web. Okay, let me push this. So it is by default going to docker.io, then it is going to my repository Harish Gowda 84, and this is the name of the application, name of the image which I am pushing. Okay, So it is preparing all the stuff for pushing it to the Docker Hub. So let us wait for some time. So now you can see the image has been pushed to the Docker Hub. You can see all the layers have been pushed. Let us go to the Docker Hub and let us refresh this page. Yeah, so you can see here, Spring Web as an application has been pushed to the Docker Hub. So this is a command which I was trying to mention. You can pull any images using the Docker pull command, and also you can push any image in the Docker Hub using this specific command. And in the Docker desktop also you could see which of the images are present locally in your machine. Let's say I have created this one. So this is Spring image latest image which is there, and you can also see all the layers here which are being used for creating this specific image. Hello, let's learn about Docker container. So earlier we learned about Docker images. So Docker images actually included the application code, all the runtime, and all the libraries and dependencies. So we have packaged everything, but it is still not running. So we have to run it as a container. So a Docker container is nothing but a running instance of a Docker image. So in image, we have a blueprint of what we need to run, and container is nothing but the living running process which is created from that blueprint. So I have the Docker desktop on my machine. So let's run some containers. So let's go to my CLI. So let us run. Let us check if we have any images here. So we don't have any images running here. So let's run the Nginx image. Okay, so the command here is, okay, so first of all, to run it as a container, we need an image. So we can specify the name as an image here, and we can specify the name of our container which we want here, and we can -d means we have to run this container in a detached mode, and we have to run this on this specific port. So what does port mapping means? The first one is the port of the host, which is our machine, and is the 80 is the port number on which this container is running. Okay, and we can give any name for that. So let us run this command. Okay, so docker run it in a detached mode. Let us give it a name. Let us give it the same name, Nginx, and it is running on port. Let's run it on port 9000, and it the container port is 80, and the name of the image which we are going to download from the Docker Hub is this one, Nginx. Okay, so let us run this. So it is trying to find the image if it is present locally. If it doesn't find the image, it goes to the Docker Hub and downloads that specific image. Now you can see the image is downloaded successfully also, and it is running. Let us check if the content is running or not using docker ps command. Now you can see here this specific container is running, and you can see here that it is created 40 seconds ago. The status is up here, and it is running on the host port of 9000, and the container port is 80. So I ran this on my local desktop. Okay, you can see on this specific 9000 port, we have this Nginx running. So can we create one more container for using the same image? Yes, we can do that, but for that we have to use a different port number. So for example, now if I want to have one more container running with the same image, I can use a different port number. And since this image is already downloaded, it won't take much time. You can see. Okay, so I guess We are having issue here. Okay, I think we have to use a new other name for this. Okay, so we can use, let's say, nginx2 here, and we can see this container is. Let us check again docker ps, and you can see we have two nginx running. One is running at port 9000, other one is in 9001, but it is both are using the same image, the different container. So let us check this out. Let me duplicate this, and let me just put it as 1001. You can see here, but this one is running on port 9000 and this one is running on port 9001. Okay, so can we, how to stop this container? So to stop this container, you can use stop. Either you can mention the name of the image, or you can just mention this ID, container ID. So let me just use this. So I'm just stopping it based on the container ID. I'm just stopping the nginx 2 here. So it is stopped. Let us check whether it is stopped or not using docker ps. You can see this is not coming now. Only nginx 1, nginx is there. So let us see here. This is port 1000. Let us see if it is. See, it is stopped now. We can also start it again. For example, using the same thing, like let's say docker start nginx 2. Right. This is the name of the container which we can provide, and we can again start it. See, this is started again. This is started with the new container ID. Let us check if it is coming up here. Yes, this is coming up. Can we restart it? So restart means that we have to start and stop again. So for that purpose, we can use docker restart the nginx 2. Okay, so let us do this. So this is actually starting and this is stopping and starting again. So let us check this again. So you can see the container ID is the same, it has just restarted it. And you can see here, it remains the same here. We can also check the logs of the container using docker logs, and you can just mention the name of the container or the container ID, and you can check. You can see this is coming in this manner. You can check all the logs this manner. If you want it in the tail mode, you can do -f, and you will see that all the logs in this manner. Okay, now you can also see if the docker, all the containers which are not being used. For example, these are all the containers available. Let's say I stop this container. Okay, and do docker ps. Only the running containers are being seen here. To check all the containers whether they are stopped or running, you can do -a. Here we will see all the containers whether they are started or stopped or running. For example, here it is exited already, so it will show all the containers which are there. So how do you delete the containers? You can delete the containers using rm command. And if it to delete the container, it has to be stopped first. So since this container nginx is already stopped, so we can just remove it. It will not show an error. See, this is removed, and if I do again check whether all the containers, we can see earlier the container was there, so the container is deleted now. To actually remove the container which is already there, which is running, for that we have to use something which is called as docker rm -f, and then we can just mention the name of the container. So this is going to remove the running container. Yes, ideally, if we don't specify this -f flag, it is not going to. So if I just try to remove this without using f flag, okay, so it is going to give me an error that this container is already running. So you cannot remove it. You have to stop the container before removing it. So you have to do a force remove here. So what we can do here is you can do -f, and you can just have to remove it. So now we can see we don't have any Docker containers available right now. Okay, there is one more command which I wanted to discuss. So this is the list of commands which we have studied, that Docker PS is going to list all the running containers. It's going to show all the fields here, the metadata, and to list all the containers including running and stop containers, we can use Docker PSA. You can stop the container using this Docker stop. You can start the container using Docker start. You can restart the container, which is nothing but stopping it and starting again. Docker logs can be used to view the container logs, whether if you want to find any issues, whether the app has crashed or service not responding, so you can use this. Okay. Also, if you want to enter the container, right? So for example, let us run it again. Okay, so let us run this again on. Okay, let us run this Nginx and let us run this on port 9000. Okay, so the container is running. So let's say if you want to go in the bash mode, within the we have to see all the files within the container, so we can use this command. Okay, docker exe minus it. Then we have to mention the name of the container, and then mention the whether we want the bash mode or the shell mode, right? So let us mention the name of it, Nginx, and let us go for SSL. You can see we have entered the container here. You can see the list of all the files here. You can see all the files within the container here. So we have to go into home, or so this is so also if we go to the Docker desktop here, we see the which of the container is running here. You can see what are the images used and what are the container running here. So we can just enter here also, and we can see with the logs here. We can inspect the logs here. So you can see the logs here and all the files which are there within the container, okay, which we saw by this command here, right? By entering using the executing exe command. So you can also go inside this way also, and yeah, any stats regarding the container which you want to study, like what are the CPU utilization or the memory utilization, we can also go from here. This is also called as an inspect command. We can get the metadata of that specific container, what is the state of the container, and whether what volumes are being used here, or the port binding, all the information we can use. So we can, okay, to exit this, we can exit it this way. Okay, it has exited. So let's say you want to do an inspect of that container which we are running. So let's inspect this container which you're already running. So the data which it is shown here, right? It is the same which is present here in the Docker desktop, right? So what is the state of it? What is the image used? And what's the network config? What is the network mode? What are the port bindings here? And if at all any volumes are being used. So all the metadata is being shown here in this Docker desktop using. So it's the same command. Docker. You can use Docker inspect here to get the metadata of that specific container. So that is what to inspect the full container details, right? Whether the IP address, volumes, environment variables, network details. This mostly used for debugging. Okay. So you also seen how do we remove the container using remove command, and we also seen that it is only if the container is stopped we can remove it. To forcefully remove any running container, we can use this rm command, and we can also use this command like to remove all the stopped containers at one go instead of removing one by one. So you can use docker container prune. So let's say, so right now we don't have only one container here. Okay, so let us stop this first, and okay, we have stopped it. So but you can see since this docker is container is stopped, okay, it is still present here. So we can use docker prune container, or is the other way around? Okay, it's other way around. So it's docker container first, and we have to prune. So it is going to ask you whether you want to remove all the stop containers. You mention UI, then it's going to remove all the containers. Then you can see here everything is gone. but we still have the image. All the containers are deleted. So we can also check the status of any resource usage which we already saw using Docker stats. I think that's it. I hope this tutorial was very helpful to you in understanding Docker containers. Thank you. So let's learn how to run MySQL using a Docker. Okay. So why do we need MySQL in Docker? So traditionally, when we try to install MySQL directly on our system, we face some issues. We have to deal with OS specific setup, version mismatches, and some cleanup issues when uninstalling it. So Docker solves this by running the MySQL inside the container. And inside the container includes the MySQL server, all the required libraries, and it runs in an isolated environment. So let's see how to run MySQL inside the container step by step. So to run it as a container, first of all, we need an image. So we will pull the image from the Docker Hub, right, using this specific command, which I've already done. And you can see I've already installed it in my locally. So you can check the images using Docker images here. So you can see I have already have the image. Okay. So how to run this image as a container? So for that, we have to use this command. So if you see this command here, okay, we have to use docker run and we will run it in a detached mode. We have to give it as a name, as a MySQL container. And then also we have to specify what is the password, the root password for logging in. We mentioned the port number here. First we mentioned the host port number, and then we mentioned what is the port number on which the MySQL is running inside the container. And then we mentioned the image which you're using to run it as a container. So that is what I have mentioned here, which I'm like -d means run it in a background mode. Okay, so let's run this command. Docker run. Let's run it in a detached mode. Give it a name. Give it MySQL container. Okay, let's run it on port number, let's say 3301 on the host file system, and 3306 is the port number on which the MySQL is running inside the container. We also have to also specify the environment variable. So it is MySQL root password. So let me give it a same password as root, and let me mention now the MySQL image name .0. So this is a complete command which I have specified here. I'm running the same command here. So let's see if this container is running. Yeah, the container is running. So within the container, to check whether the MySQL has started correctly or not, right? So we can check this container status, and then we also can check the logs. And within logs, we have to see this command that it is ready for startup. So we can go to Docker desktop directly. Okay, and you can see it is running as a container here on this 3301 port number. Okay, so let's go inside it, and then we have something called as a logs here. So let us wait for some time until and unless we see this specific log here. So now you can see we have this log here, this specific one, MySQL in process done, it is ready for startup. So after waiting for some time, we have got this log here. Okay, so so you can see this specific log here. We have it is the same. So we have MySQL running inside the container now. So as a next step, what we can do here is we can connect to this MySQL inside the connector, inside the container. So how do we connect to MySQL inside the connector using this command, docker execute, and we are running it as an interactive mode. And then we mention the name of the container. And then we run this MySQL command, MySQL minus u, we mentioned the username and minus p. After after doing this, it is going to prompt us for the passwords, and then we're going to give the password here. So let's run this command. Okay, so let's run this. So let's add the password, and you can see we are inside the MySQL here. So let us type some command like show databases, and you can see we are getting the list of all the databases here. Also, we can perform some operations like, let's okay, let's create a new database this way. So create database test db. You can see the database is created, and so using this database we have to mention use that test db. Okay, so the database here is changed. So let's run some commands here, right? Let's create a table here. Table is created, and let us okay, insert this into that specific, insert this row in the table. Let's do select star from users. You can see the row is inserted. So we can see that MySQL sync is working fine. Okay. Now, so here have seen that we have created the database manually, and then also we changed to that specific database, and then we did all this DML operations here, right? So there is one more options. If you see this command, right? So most of the things remain the same, but we have two other things. For example, let's say the database. So if you mention this environment variable before creating the container, then we can mention the database name here, and also we can mention on which user you want to use that database. So this is the only different thing. So this, what it will do is it will automatically create the database for you, and we will have to also create a user for you in that database, and that specific username password here is this one. So if you see here in this command which you mentioned, we have MySQL root password, right? So if you see here, it is not root password here, it is MySQL password. It is belonging to this specific user which we have created, which is a non-root user. It's not a root user. So ideally, these are three things which will be different here. So this is for the root password definitely, but this is, we can just create a database automatically, and within the database we can just create this user and this password also. This also we can do at one go. Okay. And also, if we can stop the container, start the container normally. So let us see what happens if we stop and start the container and see if the data is still there or not. Okay. So what I will do here is I'll exit from it. Okay. Now what I will do is let's go to Docker PS and Docker stop MySQL container. Also, we can check in the Docker desktop also. Okay, so if you see it has stopped now, right? And we can do start MySQL container and do a start here. So it has started. So you see it has started now. Let us go inside and see. So yeah, so I think it is still starting the MySQL server with inside the container. So let's wait for some time. So MySQL server has started. So let's check again. So let's check again if you are able to see the data after starting the container. So we'll just go back here and again use the same command which you have used earlier, right? This is the same command which you used to get right into the container. So we'll use the same command again. Docker exe. You mentioned the password, and we have we are inside the MySQL. Okay, so let us check the databases. So we can see we still have the test databases. So we'll just use two test DB, and we have the database. So select star from users, right? Yeah, users. Yeah, we can see we can still have the data. So even if we do a start and stop, the data remains there. Okay, so let us exit from it. Okay, so we have seen all this command, and let us discuss about data persistence here. So only if you do stop, start, and restart, the data remains there. Okay, so only do if you do a stop, start, and restart, the data, even if you are restarting everything, the data inside the container remains. If you are trying to remove the container, right? If you try to remove the container, then the data is gone. So let us try to understand this concept. Okay, so to avoid that, right? So we have to do what we have to do is we have to create a volume. So by default, all the MySQL data which we have created is stored inside the container. So if the container is removed, the data is lost. Okay, so let us try to understand this concept here. So okay, so to avoid that, we have to create a volume using this command, and we have to, whenever we are creating any container, we have to specify the volume here, right, which we are going to mount, and for this specific. So let's understand what this command is trying to do here. Okay, and so yeah, so the first one here is the MySQL data, the volume which we have created. So this is the Docker named volume, okay, which we have created, and it lives on our host machine. Okay, it lives on our host machine. It is managed by the Docker itself. Okay, and it persists even if the container is deleted. Okay, so now what is this path? Okay, slash var slash lib MySQL. So on a normal scenario, this is where all the MySQL data is present. So MySQL stores all the data here, all the databases, tables, indexes, and user info inside the container. So Docker says, so whenever MySQL writes data into this specific path inside the container, so when we specify the volume, actually it is going to write inside the MySQL data volume on the host. So the container becomes stateless, but the data remains same. So whenever it is trying to write into this is path, it is going to write into this volume which we have specified. So if you just go to this specific path here, right, in the MySQL itself, and we go to files, so if we go to var and lib and MySQL, so this is a path where all the data by default is stored. Okay, all the MySQL data by default is stored. So once we create the volume, the date, all this data is going to be stored in the volume. Okay, so to do that, let us create one more container. Okay, Docker run. Let us run it in detached mode. Let us give it a new name, MySQL volume. Let us give it a name, MySQL volume, and let us run this on port 3302, 3306, and let us give it an environment variable MySQL root password is equal to, again, root will give, and then we have to specify the volume name. Okay, so let us go back here and see what is the command back here. So if you do see here, we have to mention the volume which we have created, and then we have to mention the path, this path. But before that, we have to create a volume. So let's create volume first, and then we'll go back to this. Okay, so let us not run this command. So let's create this volume, MySQL data. So we have created the volume. Let us run this command back. Okay, so let us run this docker run -t name MySQL volume as the container, and let us run this on port 3302. 3306 is the port number of the container inside, and we'll mention MySQL root password is equal to root, and then we are going to give the volume name here. So what the my volume name is MySQL data and we have to give this path, which is slash var slash lib MySQL, and this is the path we need to mention, and then we specify what is the image we are going to use, right? Okay, so let us run this command. Okay, since we have created a new container, so let's go back to the here. Let's see if we have any volumes here. So see, we have the volume MySQL data which we have created here, and at this time it doesn't have any data per se. Okay, so let's go to the container. So we have this MySQL volume container. Let's go inside and just inspect the logs. So let's wait for some time until this it is initialized. So now we can see that MySQL is running inside the container. It has already started. So let us go back here and let us see which Docker process, Docker PS, and we have both the containers running here. So let us go inside the Docker volume container using minus t container MySQL volume, and then we have to run MySQL minus user root and minus password. Okay, so root. So we're inside the container. So here we at this moment we have not created anything in this specific container. Okay, so let us create some tables inside this container. So let's create this again. Okay, and let's create this database, and also let's use this, and also create the same table again in this volume also, and so it is created. So now let's create two users here, Jim and Tim. Okay, so we have this user, select star from users. So we have this two users created in this table. So let us exit. Let us see if this is present here in the, just go to MySQL volume, and we have files here. So if you see here, it is also showing the volume, that it is also stored in the volume. If you see this tag here, that so we have mounted this. So if you go to the volumes back here, and if you go to MySQL data, and you can see we have all the data related to the MySQL here inside this specific volume. Okay, so let us try to remove this container and then create one more container with a different name and see if we are able to get the data again. So we have Docker PS. So we have Docker remove forcefully. So let us remove Docker, sorry, MySQL volume. Okay, let us remove this, and we can see here that in the container we don't have that volume again. So let us create one more container, okay, which we have used earlier. So we are going to use the same thing, but let us give it a new name here, persist, different container, and we are using the same password. The volume remains the same, right? And let us see if we are able to get the data which we have persisted in this specific container with a different name. So we have MySQL persist running. Okay, So we can see the MySQL persist is running here. We'll just go back to it. And so let us wait for this to get started. So MySQL is running inside the container. So let us check now. So, we'll use the same command, docker exe, and here we will mention the name of the container as persist. Okay, and we're going to log in inside it. So let's use the root, and we have logged in inside the MySQL. Please note that we have created this new container. Let us see show databases. Yeah, we can see we have the test DB as it is. And let us see select star from users, right? So we can see we have the data as it is, even though we here in this specific step, we have gone and created a new container and we have used this volume, same volume on which we stored the data earlier. And right, and you can see here also, we just go and inspect the files here also. We'll see here, see in the slash where slash lib. You see, this is showing as a volume is mounted at this specific path. So you can see it's already clearly mentioning it here that we are using the data from this specific volume view. So we have covered all the topics here, starting, stopping, and removing the container. Data persistence here also we have covered, and we also explored what this specific -v command means. This is the Docker volume which we have created, and all the concepts we have already covered. Okay, so these are some of the other Docker level commands. Like, for example, if you want to view the Docker logs on your terminal, you can use Docker logs and inspect the full configuration of it. We can do Docker inspect here. And this already we have explored executing this inside the container. Also, if you want to understand the stats of the container, we can use the same thing. It is similar to what we have seen earlier for logs and inspect here, right? This is what these commands are trying to do. I hope this tutorial was very helpful to you. Thank you very much. So let's understand how to Dockerize a Spring Boot application. So what does Dockerizing a Spring Boot application means? It means that you can package your Spring Boot jars and along all with the Java runtimes inside a Docker image, so that Docker image can run consistently in all the environments. So currently I have a simple Spring Boot application here. So it is having a controller here, like it's a very simple one. So at this specific endpoint, it is just going to return whether the system is up and running. Also, I have the application.properties where I have mentioned what is the properties, what is the port number here, and what is the name of the specific application. So if you run this application here locally, so we'll get it in this the output as system out. Okay, so now what we are going to do is I'm going to just stop this application now so that I can run that in a Docker. So okay, so so what is the prerequisite for this Dockerizing a Spring Boot application? So we should have a Spring Boot jar. Okay, so for the Spring Boot jar, if we go to this target folder here, I already have that Spring Boot jar. So how to do it? We have to run it. We can run Maven package here to generate the Spring Boot jar here as a command, or you can just directly do it from here from the IntelliJ. Okay, so this is what we require. We require a Spring Boot jar which we can run it, get it through Maven, and also we need to have a Docker installed, which I already have it here. Docker is installed on my desktop. We have Java runtime 17 present here. So typically a Spring Boot application should have this specific structure. Okay, so I have this as source here. Okay, and within the source, then I also have the Docker file here. Okay, this is very important. So we'll just come to this point later. But for the time being, this is how it should look like. So as I mentioned, how do you build a Spring Boot jar using a Maven command, Maven clean package? We can run this command and we can get the jar. We can get the Spring Boot jar. So in our case, the jar name is something different in the target folder. It is like Spring Web Snapshot jar. Okay. So this is how we can get the jar. And then we have to write in a Docker file as to how do you run the instructions. So for that, we have to go to the Docker file here, which you have written here. So we'll take a base image from the Eclipse terminal. Okay, so what is that? So just nothing but a Docker base image that contains a Java 17 runtime environment. Okay, we have mentioned Java 17 as a runtime environment, and it is maintained by the Eclipse terminal project. So basically, this image internally contains Java 17 JVM, all the standard Java runtimes libraries which we require, also very minimum Linux OS, okay, and all the security patches in applied. So just a base image which we require. So this is how the Docker file will look like. And on top of that, we are going to create a working directory, and also we are going to copy the jar which you are having here, right? So if you just go here, we have the target folder. Within the target folder, we are having this specific jar which we generated in the target folder here. So this we are going to copy it in the app folder here. Okay, and then we are going to expose port 9000, because if you see here in the application.properties file here, so our application is running on port number 9000. So we're going to expose that port here in the Docker file. So once that is exposed, then we are going to run this command as an entry point so that your Spring Boot application is up and running. So let us first, using this Docker file, let us first create an image. Okay, so right now, based on this, as I already explained this commands back to you, and so we're going to run this Docker build command to create an image. Okay, so we have something called as Docker build. We are going to give it a name. Let's give it a name, Spring Web. So it's going to pick the Docker file from the current directory. So I am going to mention it as the current directory here. This is the command which you need to check. So if you see here, all the instructions were run step by step. First, initially the base image was downloaded, then the working directory was created, then our Spring Boot application, Spring Web jar was copied to that specific directory. So let us see with the Docker images are created using Docker images. You can see we have the Spring Web as the image here. So we have the image created now. So now we have to run it as a container. So for that, we have to use this command. So we have Docker run it in detached mode, give it a name to the container. I'm going to give it a Spring Web, and also the port number. As I mentioned, this is the local port on which I want to run, and this is the container port on which our Spring Boot application is running inside the container. And then we have to give the name of the image. So here I've kept the container name, the image name the same, but this is the image name and this is the container name. So let's run this. Also, we can go to the Docker desktop and check whether the application is running here or not as a container. You can see it is running here on this specific port number. So also we can just go to this port number and check whether it is coming up right now. So let us run it in a different. Let us duplicate this and check if it is coming up. You can see now the system is up and running, and I don't have anything running locally at that specific port number. It's purely running in the Docker itself. So that's it about how to Dockerize your application. I hope you have understood all the steps which are mentioned here. So like how should your Spring Boot application structure be, and what are the prerequisites? We need a jar which you can generate using a Maven. Install all the Docker application. Once you generate the jar, you write your Docker file and take the base image from the Eclipse terminal, and then copy your jar into this target folder, expose the port and run it as a Spring Boot application. And once you have created the Docker file, you create a Docker image using it. Once you have created the Docker image, you can run it using a Docker run command. Also, you can check whether the Docker is running or not using Docker PS. Here you can see that Spring Web application is up and running, okay, as a Docker. And about a minute ago, and you can see the port numbers on which it is running. So let's learn what is a Docker multi-stage build. So to understand what is a Docker multi-stage build, let's take an example of a Spring Boot application. So I have very simple Spring Boot application here with a very single health container, which is going to mention whether the system is up or running. That's it. And we have a Docker file here. Now, if you see this Docker file very carefully, it has two type of instruction. One instruction is to build this project, and other instructions are there to how to run this project. Okay. So whenever we are trying to build any project within our Docker file by giving such instructions, so we have to get a very big base image. Okay. So this base image has two parts. First, it is having all the build tools, and the other part, it also contains the Java 17 runtime environment as well. So this is a very big base image which we are using, and also we are copying all the source code inside it, and then we are running this specific instructions. So once we generate the artifact, right, and generate the base image generate the image out of it, it is going to be a very big base image. So let us understand it again using a very simple diagram. So we have taken a very big base image here, okay, which is containing all your build tools and the Java runtime environment. So it is having the compiler, dependencies, and all the tools. Then we have the source code, and using that source code and compiler, we are going to generate the artifact out of it. But the image which you generated is going to contain all your compiler, source code, and the artifact. But in reality, you only want the jar file to run your application. So, so that's the reason we use multi-stage build. So we'll come back to this definition later, but what it is trying to say is, so instead of using the entire big base image, we develop this in a single step, and using the artifact which is generated in this step, we are going to use it in the next step. Okay, so we'll demonstrate this using it on the Docker file. Okay, so but as a definition, we use multi-stage builds to create small, secure, and production ready Docker images by separating the build environment and the runtime environment. So let us build this image, and let us see the size of the specific image. Okay, so I have a Docker desktop here installed on my machine, and I'm going to go to this project directory, and I'm going to build the image. Okay, Docker build -t. I'm going to name it as, like, a single web. Okay, and I'm going to use a specific Docker file. It should be build. Okay, so let's run this. So okay, so this step took some time. You can see here all the instructions being executed, like, copying the source code, running, building this project specific app actually took around 83 seconds. So you can see all the instructions are run successfully. So let us see the Docker images here. Docker images, and you can see the Docker image which is built here, and the size of that image is 590 MB. Okay, and also you can run this as an application. For example, you can use Docker run it in a detached mode. I will give it a name as single web only. Okay, and I will run it in the port 9000 on my local host as 9001, and so it is running on 9000, and I'm going to use the name of the image, which is single web. So let us run this. Sorry, there's a typo here, so I'll just make it as single web. So let us check if it is started. Docker ps, and we can see this is running on port 9001. So you can just test it out locally. You can just go here, and you can use 9001, and you can see the system is coming up and running on 9001. So let us stop this using Docker stop, and let us go back to the discussion which we had earlier. So we can see that a single image, which is a very big fat image we took, and we went through all this instruction, and we could see that it is a very large image. It's having Maven, JDK, and all those dependencies, and it's also security risk because we are including the build tools. And the startup also will be very slow because the size of the image itself is very huge, and it violates the least privilege principle. You can see the image it here. It is like earlier I mentioned here the size of the image is around 590 MB here. That is what I was trying to mention here. Okay, so these are the problems with using a single stage build. So let us now move to the multi-stage build. So we are going to replace the Docker file using this instruction. So let us go through it one by one. So let us copy this, which I already created, and we are just going to paste it here. Now, if you can see, there are two set of instructions here. First step again is going to do a build. Okay, but in the next step, we are going to utilize the artifact which is generated in the earlier step here. So let us go to each of this step again here. In this instruction, we are using again a very big fat image, but you're mentioning as built. So we're going to use this only for building the package, not while running it. It won't be included when we generate the image. Okay, then we are using a new work directory as build, and then we are going to copy this pom.xml into this specific directory. I'll explain this step in the documentation. Then we are going to copy all the source code which is there in this specific folder dot source, and then we are going to run the command to build the package. So this is the first step, right? So let us go to the documentation here. Can you actually? So as a stage one, we are going to use as build to illustrate that this is a build step. This should not be included in the final image. So we have all these parts here. It includes the Maven as well as the full JDK, and we are going to mention this as a stage of the build. So this stage is not going to go into the production. That means as a final build. So we are going to copy pom.xml here in this. So what is the meaning of this specific statement here? So this, when you run the statements Maven dependency go offline, it is going to download all your dependencies upfront. Okay, so only when the pom.xml is changed, the dependencies are going to be re-downloaded. If your only code is changing, then only all the dependencies are reused. It's not going to download it again for you. And if your pom.xml is unchanged, it is not going to do a re-download again. So this is a step wherein for optimization purpose, we use this specific step. So the next step is very simple. We just copy all our source code inside this, and then on top of that, we run this specific command to compile it. It's going to compile it and it is going to run any test, and then it's going to produce this this specific jar which you want. Okay, so this is the first step which I wanted to mention here. So if you see, this is the first step, and this is all the Maven and the build tools are not going to be included in the file. So as the next step, right, we are going to use a very slim base image. So this doesn't include any Maven tools. If you see the name here, Maven 3.96 Eclipse Terminal. So this is only very slim image which contains only Java runtime environment of version 17. So here we're going to choose a new working directory, and then what we are going to do here is, so whatever we have done a build here, so in this specific path, right, we are at this specific path we ran this package. So on this specific path /target, all your Spring Web, the jar is going to be created using this command. So we're going to use this jar which is created in this step, like from build step, right? And you have to go to this path, I have to copy it in apps dot slash. So basically this step is just to copy that jar, and we're going to use this jar to create the image. So basically the image is going to create it from this step itself. Okay, so it is going to be very small. So if you see here, only the purpose of this is to build multi-stage build is to copy what is generated already in this build step. So this is not going to be included in your final image. So let us run this again. Okay, this time we are going to do a build minus t, and you have to mention this multi web, just to give it a different name, and then you're going to use a Docker file which we have updated this. So let us run this. So we are done with the building of the step. So you can see all the steps which are executed here, right? Right, like copying the pom.xml, again running this dependency, and then again running the build again, running the step to build the project and copying it. So let us check the Docker images. You can see the size of the image has reduced significantly. From 590 it has gone to 284 MB. So this is a stage 2 which I was explaining, that we have taken a very slim image, and it is only a GRE, it doesn't contain any compiler. It's of very smaller size. And again we executed this step. We have copied the artifact from the build stage by using this command from build stage, and then we went to the specific location and then copied it here. And okay, this step, as I mentioned, this copies a judge. All your Maven tools, source code, and the cache all are discarded. The final images is clean. So if you see the more or less, this is just approximation of steps. So in our step, it was like from around 600, it went to around 284. Okay, so I got a 50% reduction. So normal you can get around around 75% reduction in the size of the image. So also we can run it as an application using the same build, okay, and which we have generated. Okay, we can just do this step as well. So we can use Docker run right in a detached mode and give it a name like same name. I'll give it multi web, and then I'm going to run and port, let's say 9002, and I'm going to use 9000 uh, port of the Docker, and then I am going to give the name of the image, which is multi-web here. So I think this should be fine. I think should use double quotes. Okay. Okay. Let's run this. Let's check it out. So it is running a 9002 port number. So let us go back here and check 9002. See, it is, so you can see now at 9002 also it's running up and running. So in the Docker desktop also you can just go and check your images here. We also here and see the size of the images here which has been built. So yeah, so there are some benefits. Definitely we have a very smaller Docker image, so all the build tools are discarded, only the final app is kept. Since it is doesn't have any build tool or a source code, it is much secure and fast developments deployments, because the image sizes are very small and it starts fast. Clean runtime environment, so we'll include what is needed like GRE and jar, very easy to debug and maintain. And also we are following the best practice because we are separating the build and the run responsibilities. Okay, and since the size of the image is low, uh, we have it is going to take less storage and less network transfer. It's ideal for CI/CD pipelines where we are going to build once and run anywhere, and it is consistent and reproducible builds. Definitely, it is avoiding unnecessary files, no source code, and all the build tools. It's production ready images because they are lightweight, they're very stable, and very secure. So let's learn about Docker volume. So any data which you store in the container is temporary in nature, right? So so let's say we have a Nginx container in our system, and Nginx container is having some data stored inside it. The moment this container is deleted, the data which is stored in the container is lost. So that's the reason the containers are ephemeral. That means anything stored is in temporary. So how to ensure that the data which we store remain persistent? So that's where the Docker volume comes into picture. So Docker volume is a persistent storage mechanism which is managed by the Docker that allows data to survive the container deletion. So why do we need Docker volumes? Because the moment the container is deleted, the data is lost. And we may want the data to live outside the life cycle of the container. And you may also want multiple containers to share the same data. And also it is useful for backup and restore. Okay. So let us understand how to create this specific volumes. So these are the commands to create the volume. So we have to mention docker volume, create my volume, and for listing we use docker volume ls. So let us run this commands and try to understand how to create the volumes. So we have here docker volume. Then let's say we want to create a volume for an Nginx. So let's say I mentioned Nginx volume. So you can just mention any name. So this is going to create the volume to check which volumes are present in your Docker system. You can mention Docker volume ls. So this is showing the volume which we just created. So we can also inspect the volume. Also we can remove the volume, but for the time being we are not going to remove any volumes. And if you want to remove all the unused volume, you can use docker volume prune. So let us try to understand this with an example. So let us have an Nginx server in our system, and let us run that Nginx server without any volume. So for that we have to use this specific command. So let us say we have docker run. Let us run it in a detached mode. Let us give it a name like Nginx, and let us run this on port, let's say 9004, and it is internally running on port number 80. And let us have the Nginx image, which is the latest image which we can use, and this is going to run the Nginx. Okay, so let us run this. So we had already had the image locally, so it is just going to take that image. So for example, we had already had the images locally, so it has used that image, or else it is going to download from the Docker Hub. Okay, so we have the Docker Nginx up and running on this specific port, which is 9004. Okay, so let us go to that port number here. So 9004 is, let us run this. So we can see we get the welcome page of the Nginx. So let us try to modify it. So let us try to update the index.html of the Nginx. Okay, so for that we have to go into the bash terminal. So for that we have to execute this specific command. So we have like docker execute. Let's mention the name of the container, and then let us go to the bash terminal here. Okay, so we're in the bash terminal. So let us go to that specific directory here, which is this one, which is /usr share. Let's see what are the volumes present here. Then we can have to go into the Nginx. Okay, we have the HTML folder, and within that we have the index.html file. So let us update this. So let us add something like this. Let us mention simple like hello world. And let us update this index.html. Okay, so I hope this is updated, and you can also do index.html. You can see, yes, it is updated. So let us go back and let us refresh this page. So we can see we got our own custom index.html. So we have this. So let me delete this container and then again create the container, and let us see if we can get the same index.html or not. So we'll just exit from this bash here. Okay, and we'll do docker remove -f nginx. Okay, so this is going to remove the container. Okay, you can see we don't have the container now, and we can also check here. So this is not running now. So let us again try to create the container again. Okay, and let's see if we again try to create the container, and let us see if we can have the same thing again. Since we already deleted the container, it won't be there. So it has again created the container. Now obviously since we have deleted this, we won't be able to see that welcome hello world here. We will get the custom nginx image again. So this showcases that the moment you delete the container, whatever you stored inside the container, it is no longer there. So for that purpose, what we can do here is, okay, since we removed the container, the data got lost. So what we can do is we can run the container with the volume, okay, and then delete the container and then check. For that purpose, we already created the Nginx volume, right? So we have already have the volume Nginx here. We already have the volume. So let us use this volume. So what we'll do here is, so here while creating the container, right, we can mention the name of the volume here, Nginx, and then we are going to mention the name of the path which we want to mount or replicate. So what is this specific path? Okay, so this is nothing but the default root directory of the Nginx. This is a folder where all your HTML, CSS, and JavaScript files or images are stored. So in simple words, what we can do is when we try to access this, right, so it is going to internally look at this specific file. So since we are actually updating this specific folder, so we want that any data which is written, which is written here also should also be replicated to Nginx. So let us go to this diagram here. So what we are trying to say is we have created the volume. So we are going to link. So we are going to link the internal folder, which is the HTML here, to this specific volume. So even though this volume, this content tomorrow gets deleted, the volume will remain there. And again, if you again create one more container representing a different color here, so that specific container can again access the data which is stored in this specific volume. So that is what we are trying to achieve here, right? So here, what we are trying to do here is we will mention the name of the path. Okay, for example, this is the name of the path which you mentioned in the document here. Okay, user share nginx html. So we're going to take this path and mention it here. Okay, and let us run this. So what is going to happen is any data update which is going to happen inside is also going to update in this specific Docker volume. So let us run this and try. Okay, it is telling that it is already in use. So okay, so let us do one thing. Let us create a new container nginx1. Okay, and then run it. So we have nginx1 running, and I think we have the container which is already running. So we are going to remove those container nginx, right? We're going to remove this first. Okay, we have removed this, and so let us run this again. Okay, and let's see. Okay, so we have the nginx running on this port number, so but with a volume. Okay, so let us go back here. So we have again the same custom HTML. So what we'll do right now is we'll again go into the bash cell of this. Okay, and update the index.html here. So we're again going to the Nginx, and we're going to the bash terminal here inside, and we're going to go to user share, sorry, visar share cd Nginx, and go to HTML folder. Okay, now we have the index.html. So echo, then we have here updated this. Let's go back here and run it. So we have gotten hello world. So let us now, what we need to do here, so let us now remove this. Let us exit from this bash. and we have to remove this container again. Okay, nginx. So we have right now deleted this specific container, so we can just check this out, and this container is no longer available. No longer available. So let us create this container again, and let us see if we can get the hello world again. Okay, so we're going back to the same command here, and we are again going to use the container. Again, we're going to use the volume which we created earlier, and this had all the data here. Okay, so let us run this. So we have the container up and running again on the same port number. So let us go back here. We can see we got the hello world now. We didn't get the custom Nginx hello page here. We got the hello world which we are actually stored in the volume. So you can also go to the Docker desktop. So you can see the container is up and running. So we also have a folder called Docker volume, and also you can see that we can have all the volumes which are present here, which are stored like Nginx. So all this is already present here. So it has created this specific volume. So actually we gave this as a volume name, Nginx. So it has created this volume here, and it is having all the data present inside. Okay, it is having so this is what the data shared data it is having index.html, and this is what got updated. Okay, and there is one more use case, right? So for example, okay, so we can also create a volume, and we can create two containers which is going to share the same data. So in our case, right, so in our case we are having this container nginx which is running on this port number. So let us create one more container, and let us run this on port number 905, and let us run this on port number 905, and also we can just give it a different name here, like we mentioned it as index 2. We are using the same volume again. Okay, we're going to use the same volume again, and let us see what happens. So we have created the again the nginx, and we have two nginx containers. One is on 5 and one is on 4. So both of them are using the same volume. So let us see what happens here. So let me duplicate this, and let us mention here as 905. You can see 904 and 905 are using the same volume. Even though I created a new container on this port, but I provided what is the volume. So it has used the same volume here. You see, both are having the same. So that is what I was trying to explain here, that you can have a common volume which is going to allow you to share the data. So both the containers can actually take the data from the volume, which is demonstrated by this example. So that's it. We have learned here that what is the usage of the volume, so that it is so that the data can live outside the container lifecycle, and also multiple containers can also share the data, and also we can also use it for backup and restore. And so these are all the commands which you need to know: how to create a volume, how to remove the volume if at all you want to, and how to this also is very important as to how do you mention which volume to create, which volume to use using -v. You can mention the name of the volume, and also mention on which specific folder you want to sync it. This is how you can just mention the volume while running the container. So let's get started with Docker commands. So I have the Docker desktop on my machine. So the first command which we are going to look here is Docker version. Okay, it is going to give you the version of the Docker which we are using now. And the second command which we are going to look is Docker pull command. So this is going to pull the images from the Docker hub. So let's say I want to pull the nginx image from the Docker hub. So it's by default, it is going to pull the latest image which is present in Docker hub. So let us pull this image. So after pulling the image, we can check whether the images are downloaded using Docker images. So this is going to give you the list of all images which are present right now. So you can see here this nginx image was pulled, and it is having the latest tag here. It is also going to show you the size of the specific image right here. Now we can run this image as a container using a Docker run command. Okay, so for that you have to use Docker run, And we are going to run this in a detached mode. We are going to give it a name to the container using name, and let us give the same name nginx. And let's say we want to run it on the port, so we're going to mention the port. So right now the port, the first is the host port number, for example 9001. So this is a port on which we are going to run the Docker in the local system, and this is the port on which is the container port on which this specific nginx is running internally. So we have to mention these things, and after that we have to mention the name of the image which we are going to use here. We just run this one. So we can check whether this container is running or not using Docker PS. So this is going to show you that the container is running on this specific port on your host system, and this is the container port, and it is going to mention all the other meta information like the what is the container ID, and what is the nginx, what is the name of the image, and how long and when it was created, and what is the status till now. So on my Chrome browser, you can see for the localhost 9001, and we can see that nginx is up and running. We can also stop the container using docker stop, and either we can mention the container ID, or you can also mention the name of the container. But let us take the name of the container here to mark this, and you have to mention this here. I'm going to paste this here, and this is going to stop this specific container here. And let's say if you just go back and try again, and we can see this it is no longer accessible. And again we can start the same container back, right? So we can just mention the same command, but we can just mention the start. Now you could see the Docker is started now. So let us check this again now. You can just go back and you can see the Docker is started again. We can also do a restart, which is going to do both things together, stop and start again. So we can do restart here, and also we can mention the name of the container here, mention this nginx, and it's going to restart this specific container. And you can see it has, you can see we are able to still able to access this things, right? Now we can also check the logs of this specific container using docker logs, and you can mention the name of the container. I can mention the nginx, and you can see all the logs which are there. We can also do a docker logs, and -f means follow, and we can check this logs live. You can just mention this way, and we can also see if any changes happen. We can see the logs coming here and in the live mode. Okay, then also we can do something called as docker inspect, and this is going to actually show you all the meta information. It is going to return all the information. For example, what is this, what is the container used here. It's pretty big. It comes in a JSON form, and here we can see it is going to return all the low level JSON information about what are the containers, images, volumes, and networks. So this is the image here. So all the meta information is going to be shown here in this specific JSON. Okay, so let's move now. So now also, since we are also running this Docker container, right? And we can also go into the file system of this container, right? So for that specific purpose, we can use something called Docker exe, and we have to enter in interactive mode, mention the name of the container here. Okay, mention the name of the container as nginx, and then you have to specify on which shell you have to run it. So let's say I want to check login in a bash terminal, so you can just mention this, and you can see here, right? And we are in the shell, so you can see what are the different folders are present here. For example, you can just go into usr, and you can just check all the, so you can just access the file system using this specific command, using the specific exe command. If you don't have a bash cell, you can also do an sh cell also, right? So you can, for exiting from the cell, you can use something called as an exit. So to exit then from that specific cell. Now also we can also create volumes here using volume commands. You can use docker volume, and then create. So I can just create my volume just for clarity. So this is Docker will create it, and also you can check all the volumes which are present using Docker volume ls, and you can see all the volumes which are already present here. So right now I created this volume. There are other volumes which are also present here. You can just check them out. And also we can remove the volumes. You can Docker volume, and then you can mention remove, and then mention Docker volume. It's going to remove the volume which I mentioned, which I created earlier. So we can just check. Now we can see that specific my volume is deleted from the system. On similar lines, we can also create networks. So you can check what are the networks already available here using Docker network ls, and this is going to show all the networks here. You can also create your own network using Docker network, and you can mention create, and you can just mention any name you can give. So I'm just giving the name as my network, and this is going to create the network for you. And you can just check again what are the list of networks available, and you can see the my network which is present here. On similar line, you can also delete the network using Docker network, and then you can just mention remove, and you can just mention my network here, and this is going to remove your network which you have created earlier. Okay, so now we have had a look at various commands. So let us see how do you create a image from the Docker file which you already have. For that, I have the an Spring Boot application right now here. So it is having a very simple Docker file. Okay, and this is just going to create an image because we already have created this Spring Boot jar here, and this is going to create this image using this base image, and this is how it's going to entry point is going to look like, and it is going to be exposed on this specific port. So this is just for a demonstration purpose. You can use any Docker file which you want, but the command will remain the same. So for that, we have to use Docker build minus t, and then mention the name of the image which you want to create. So I'm going to create like Spring Boot web. Okay, so I can, since if you want to push this image in your Docker hub, so you have to give the name of the repository, which is my repository is harishgowda84, and then you have to mention the name of that specific image, that Spring Boot web, right here, and then mention the path on where you have the Docker file. So my Docker file is already present in this Spring Web position, so I've just mentioned the current directory and let it run. Now we can see the image is built. We can check whether the image is built using Docker images, and we can see that we have the image which is built here, Spring Boot Terminal latest. And for that, so before pushing to the Docker, we have to log in, right? So you have to mention Docker login, and it is going to log into your Docker hub. So this is a Docker hub where I'm already logged in. Okay, I already have some images which you already pushed, so I'm going to demonstrate the same thing here, right? So after login, so now what we can do is we can do Docker push, and you can just mention the name of the image which you want to push. So it is harishgowda84, and you mention the name of Spring Boot web. Okay, I want to push this image. Now you can see that the image has been pushed. So let us go to Docker hub and let us refresh this page. Now we can see there less than a minute ago we have the image which is pushed to this specific Docker hub. That's how we push the image. Now let us have a look at some of the cleanup commands, right? Okay, so we have like images right here, and also we have all the containers, right? So let's say you want to remove the container. So for that you have to use something called Docker remove, and mention the name of the container here. Okay, so you have to stop it before removing it. So for that purpose, we will just stop it, Nginx, and then it is stopped now. So we're going to remove it now using remove command, docker. Then you can see now the Docker container is removed. You can see there we don't have any running containers right now. And on similar lines, we also have Docker images, right? So let's say I want to remove all the images For example, let's say I want to remove this image. You can use docker rmi and then mention, let's say I want to remove this nginx image. So you can mention this way, and it's going to remove all the image. But we can see we can have still have images, right? And also we have docker. Let's say if you have any containers which are stopped, none of them. So let's say at one go we want to delete all the images and containers at the system level, right? So you can use system command and you can just mention prune command, and it's going to remove everything. So this command is going to remove all the stopped containers, all the networks not used, all the images or any build cache here. So you just mention yes here. So you can see it is going to remove everything. So it is first starting to remove my image here, which is present here. Any cache present, objects which are present, it's going to remove everything here. So if you see Docker images right now, you can see nothing is available at this moment.